Some of you were in last week's talk. I talked about 400G. Yeah? 400G looks like it's inevitable that in a lot of industries right now. As you remember, one of the main driving engine inside the 400G is what they call DSP. Right? So last week I did not talk about other way to do this. Actually, there is an analog version of chip sets to work on this PAM4. Basically, PAM4 26 gigabytes technology. So today, I'm going to update you with what is happening out there, what our partner is doing, and showing you some test data as well. So it's meant to present to you like a discussion type. Okay, so, okay, sorry. This one is, I just want to show you the DSP. This is a very typical DSP configuration. Currently, all the 400G DSP transceiver use 400 GAWI 8 solution, 8 channels of 26 gigabytes, right? Which utilize their so-called 7nm process, right, for the DSP as the gearbox, because sometimes you have to translate the data ratio, and then also as a retimer for the PAM4 signal. And the signal analysis and process are performed in the digital domain. Everything is processed in digital domain. And the DSP, why it's so powerful and so big? Simply because there are some main areas I want to point out. One is the program memory. The other one is a data memory. And also there is computing engine, input, output, A to D and D to A. So that's why it comes so big. As you can see, one of the typical DSP used for 400G is like a 12 times 13 millimeter by 2 millimeter. And you can see all the there are 575 ball BGA there. So the alignment is has to be precise. So, and moving back to the left side, the block diagram, you can see very typical, right? A channel coming in, or 20 or 26 gigabytes, and there's a translation on this particular DSP to down convert it into 8 to 4. It's like a ratio of 2 to 1 into 4 channels of 100 gigabits per second. So that's why they call it 400 gigabits per second line side data rates. Coming back is the same. So I just want to show you how people use it in DSP form. Any questions? Okay. So the next one would show you roughly in current form, the 400G solution, the so-called thermal problems, right? So you can see the DSP is mounted very close to the edge fingers, right? They need to, right, to process anything from the whole side. And on this one, this is like a thermal simulation. It's like almost 5 watts. And you can see, well, the module down there is like 180-degree flip. Basically, the optics are pretty hot. But I want to point out, besides the optic, there's a DSP inside. It sucks in about almost half of the power. And on the right side, you can see there's not much room, right, to operate in this format. You can see on both sides, low temp and high temp, it goes up very fast. With this thermal analysis done with fan. So without fan, there will be almost, I'm sure there will be thermal runaway. So I just want to give you some feeling of how hot this module is. This particular one is showing you is LRH. So you can see, let's go back to the other one. So there is no translation in mux and demux. It's 1-to-1 basically on this one because they have 8 channels. So everything else is the same. So going into the next slide, I would like to show you some information of what I'm talking about. I don't know if you know, there is a group called OpenEye MSA. Basically, its goal is to minimize the need for signal processing in optical modules, and which has the many benefits as I mentioned last week. There's a lower latency by using linear CDR, lower power consumption, and lower cost. And I will show you those numbers later in the following slides. The initial focus of this committee is focused on the 26.56 megabytes, which is 53 gigabits per second PAM4 for 50G, 100G, 200G, 400G, QSFP-DD, and OSFP. So if it is released, it will benefit everybody, I'm sure. And the goal is to reduce the complexity and leverage the reliable optical compliant tests. Now it's been used for traditional eye diagram, right? In place of the T.Q. T.Q, as you know, is just for the PAM4 eye. So they would talk about eye mask margin instead of T.Q. And also last year in the conference, CIOE, MACOM, and CIG both separately demonstrate in the conference the OpenEye MSA compliance analog chipsets with the 200G QSFP plus, right? Which is instead of 8 channels, it's just 4 channels. So it was successful. It was published, and right now the chipset design are going on, and the sampling is set for the mid-2020. Now it's mid-2020. So I'm almost certain in the fall sampling would be available. Even some vendor right now can request qualification samples. So recently, our company's partner is called Optical. They have made great progress using this linear CDR for 200G and 400G PAM4 AOC. So, and also this page is like a summary of the test results, and you will see the test later on. And basically, it's done at high temperature to show its compliance. At 70 degrees C, prefab is about 5.8 to 10 to the e to the -10. And post-fab, of course, there is no error. And also, you will see some bursting error coming in, like a 12-hour testing, which is quite normal. I think the spec allows some bursting error, but not a lot when you do overnight test. So, and the product also, our partner also would be CMOS 4.0 compliance. And also the power consumption is pretty low as what the chipset promise. For 400G is about 7 watts. And for 200G is half of that, is 3.5 watts. And I want to give you some perspective to compare this number. The 100G QSFP28 AOC spec is 2.5 watts. You know why so low? Because there is no DSP. And also currently 400G AOC is about 10 watts. So you can see there's a reduction of 3 watts of the power by using linear CDR. And the reach is the same, like 70 meter OM3, 100 meter OM4 multi-mode fiber. And the latency is to be promised to be low, and our supply did not test it yet, but it will come through later on. And the cost is going to be lower than what we spend. So the first slide of the test results showing you the eye. People working on 400G are familiar with this type of eye. It's called theta Q. You can see the theta Q is 0.9 dB or so. Give you a comparison for 400G DSP theta Q, the spec is 3.5 dB. Normally, for a DSP-based 400G transceiver, it's about 2 dB or so. So you can see this is below 1 dB. You can see the big opening on 4 channels, 1, 2, 3, 4. Yeah, and the power is there, and the extension ratio is better than 2, right? The spec is 2. So this is a very good results. Going into the bit arrays, sorry about the size of this show. This slide is very hard to see. Basically, on each one of them, there are 2 modules, right? A to B, B to A, back to back. On the left side of those 2 slides, on the left side, you can barely see. One is called pre-fed. The other one is called post-fed. The pre-fed, it tells is about half of that have no error, and half that has an error about e to the minus 11-ish. Yeah, some might be minus 10. And going into the other module is the same, minus e to the minus 12, e to the minus 10, e to the minus 11, some of them 0. They just showing you the test results. And this is done 400G at 65 degrees C. The next picture shows you the long-term test. Let me see. You can see 12 hours overnight. 12 hours overnight. There are some bursting signal, right? You can see on 5, some of that. But this is allowed. It's a known issue on 400G. I think it's from the host side. It's also could be from the chipset. Maybe people are this problem. This bursting error has been there for about the last 3 years. Everybody knows about it. When they run overnight tests, it is bound to have a bursting error. So the next one is showing you the 400G, right? You can remember the power consumption is half of 400G. It's done almost the same, like 70 degrees C, bursting error check, and 100 meter of OM4 fiber, right? You can see the channel is about, only half the channel is active, right? Because the 200 gigabits per second configuration. Any questions? Going into another slide showing you the test is done like that. This is done without the fiber. You can see it's about 10 feet of jumper fiber in between, right? So just showing what it is, the test setup and so forth. And let me go back to the summary as a completion. So I want to emphasize again, at 70 degrees C, post-FET is no error, and it can go 100 meter OM4, and also the lower power consumption to be 7 watts, and low latency, low cost. So in fact, a lot of people are waiting for this type of design coming in from the lab. So I have great hope, and I think the goal of this chipset is really right on the target. Let's wait for some samplings. And that's the end of my talk. And there are some products from us, and we'll do a better job next time to screen this. So I'm open for questions. Do you have a concern? Do you have a question not clear? And I'm here to answer you. Or you can even send us text, email, or so forth. I will answer you one by one.
Eric, this is Michael. So thank you. Actually, this is
Michael.
the first time I'm hearing this in detail myself. So just to make sure I understand that on the power consumption side, you made a comparison between the equivalent 400 gig DSP based and 400 gig analog based. So yeah, compared to the DSP based, at least this sample, power consumption is about 30% less, because you know that this one is a 7 watts and DSP is around typically 10 watts. Is that correct?
Correct. That's apple to apple. Yeah, okay. Apple to apple. Okay. Well, we're comparing to the AOC, right? So AOC design is VCSEL. So yeah, it's a 30% less.
I see. Okay. I mean, this is just a for my own benefit down the road, but
yeah.
Are there any? I mean, clearly it's analog benefits. You mentioned about better latency, and clearly the power consumption is low. It's all that is good. Is there any benefit of using DSP? What are the benefits of using DSP? Is it just technically? Is there any benefits that we should be aware of using DSP-based ones?
I don't know. I personally, I have seen both, right? So, for many years, it's been CDR, linear CDR, right? And all of a sudden, there's a DSP design. But the trouble was, I always think DSP is more troublesome, right? It's simple because for analog, right? For analog, if there is a bug inside the analog firmware or hardware, the turnaround for the vendor to resolve that is less than 2 months, really. But for DSP, has to be more than 6 months. So in the industrial, at the beginning, there is always iterations, right? Because it quite didn't work. So people had to wait at least 6 months for the next version. People get very, very upset. So I have to tell you that that's one thing is due to the complexity of the DSP, yeah, and because it's a huge scale of integration. Yeah, everything. See, the other thing is, even a small, very, very small bug inside a chip, they have to redo the whole chip altogether, right? You think about that. There's so much silicon. And yeah, so for, again, as you know, Michael, you remember that the presentation we had with our partner, that is sometimes they use 2 sets, right? For the 400 and for the 200, right? So that would eliminate, if people do that, eliminate the wait time by half, right? Because you don't have to go through the whole chip, right, in order to fix a little small bug, right? there are lots of advantage of using smaller version to be more flexible in this one. So I don't know. I cannot tell you what the advantage of DSP. It maybe the processing is simpler because you can write formula.
Okay.
Yeah.
All right, good. Thank you.